Hi everyone, in this video we're going to start topic 9. We're going to be talking about solubility of ionic compounds, net ionic equations. We are also going to dip our toes into pH calculations, and we will start just a little bit of intramolecular forces, discussing why chemicals interact with other chemicals the way they do. So first things first, let's start with predicting products of a double displacement reaction. So this is kind of what you all are actually doing in your in-person lab training right now. You're doing precipitation reactions. So what a double displacement reaction is it's where you have two compounds that are comprised of different atoms. So something like NaCl is your A and your B. These are different atoms. And what happens here is their components trade and they swap. So maybe you have KBr here. And you react these together. The bonds holding these compounds are broken and then reformed such that they're energetically more favorable. And so we see these new products. What I like to think of it is that your cations trade places or your anions trade places. So if you write out this NaCl plus KBr, these are both cations here, your Na and your Cl, and they can trade places with each other, and then you find your new products, which is NaBr plus KCl. You could also view it the other way. Again, if you wanted to, you could swap the anions. It really doesn't matter. Whatever is easiest for you to remember. So you could choose your Cl minus and your Br, and you can trade those, and you'd still end up with NaBr plus KCl. And so these are our new products after the reaction has occurred. So that's what we call a double displacement or a double replacement reaction. You can see two things trading places. So typically when we look at our double replacement reactions, we do this with ionic compounds. Specifically, very specifically, we do double replacement reactions with ionic compounds, okay? The only other time you will see these reacted with something that's not necessarily an ionic compound is if it's an acid and a base. Most acids and bases are ionic compounds, so they will fulfill usually both categories. So here are some examples of our ionic compounds. Remember, ionic compounds usually have metals and nonmetals together. We've been talking a lot about molecular compounds, things with two nonmetals in them, like water has two nonmetals, or something with phosphorus and chlorine, or sulfur and chlorine, that sort of stuff. Those are molecular compounds. But stuff with ionic has a metal in it, starting at the beginning, and a nonmetal at the ends. This is an acid right here. So hydrogen can act as a metal or a nonmetal. It's a very interesting compound, so it kind of classifies as ionic, but it's also kind of not ionic. It's a misnomer. And this here is a base, but it also qualifies as metal and nonmetal. So we can have our double displacement reaction happen with ionic compounds, and it can do two things. It can either be a neutralization reaction with an acid or a base, or you might see a precipitation reaction. This is when a solid forms from two aqueous compounds. Let's take a look at our acids and bases first, and then we'll move on to what a precipitation reaction is. So this is our neutralization reaction, which is a type of double displacement or double replacement, whatever you want to call it. It's the same thing. So let's examine what an acid and a base are. So acids, we're going to go by this Bronsted-Lowry definition. There are other definitions of acids and bases, but this is our Bronsted-Lowry definition. In our case, for what we're doing, acids are strictly proton donors or H+ donors. We say proton because if hydrogen only has a proton and a single electron, it's got, so one and a negative, and if this goes away, all we're left with is our one proton. There's no electron floating around. So a proton is hydrogen, is an H plus ion. So acids donate these, they give them away, give away H plus. And bases, the definition of bases is that they accept those H pluses that are given away by the acids. So they accept them. So here are some nice examples of this. You can see here that this NH3, this is NH3 here. I'm not certain why these are here. This is confusing. We're going to get rid of this. So NH3 here, it accepts an H plus. So if you add an H plus onto here, it turns into NH4 plus, which means that because it's accepting an H plus, it is a base. In a scenario where you have, say, water, H2O, here are your hydrogens, this is your oxygen in the center here, you could remove a hydrogen, so a hydrogen goes away and gets added over here to the base, and we end up with OH. So in this case, because the hydrogen is leaving the water, it leaves / donates. That means that in this case, water is the acid. So you can always determine if it's an acid or a base by seeing where these hydrogen ions are going. If it's leaving the compounds, then it is an acid. If it is accepting it, then it's a base. Let's examine how this affects our pH. So you all may remember that whenever you have an acid, so like vinegar, lemon juice, that sort of stuff, all of these sour substances, these tend to lower our pH. So we have lower pHs for things that are acidic. They're acidic. Like your stomach acid has a really low pH because it's acidic, it digests our food for us. Alkaline pHs, higher, are usually bases. So bases have a high pH on the pH scale. Acids lower pH, bases raise pH. Now, this ties in nicely with what we were talking about with H plus ions. So if you have something with low pH, this is kind of what the environment looks like. There's a lot of H plus ions floating around. Now, if you have a high pH, we're going to have low amounts of these. Low amounts of H plus. That doesn't necessarily mean there's going to be OHs around. Sometimes it does, sometimes it doesn't, but there's going to be a lot less of your H plus. That's really what it means. So our pH is determined by this mathematical equation here. Our pH is equal to the negative log of our H plus concentration. Remember that concentration is determined in molarity. So molarity. And our molarity is equal to moles per liter. So that's the unit here. It's the negative log of our H plus concentration in moles per liter. So however many of these we have in moles per liter is going to lead us to determine our pH. So say you have, 1 mole per liter of H plus ions in solution, and you want to know what the pH is, you can simply put this in your calculator, negative log of 1 mole per liter. You end up with 0. That is a very low pH. So that is a lot of H plus ions. So most of the time, your values for pH are going to be smaller than that. So if we did 0.1 mole per liter, let's see what that is. We end up with a pH of 1. Okay. So do be wary of whenever you're doing calculations with pHs, anytime you have a concentration that's that's higher than 1 or at 1, it's probably not right. You probably aren't going to have a pH of 0 or lower than that. You technically can, but you probably aren't going to. So be wary of your work when you're calculating. Now, whenever we're looking at pH, the reason these OH compounds typically pop up is because we're looking at water. So water does this thing where it can either accept protons or it can donate protons. It does both. So it can be an acid or a base. So what that means is this hydrogen here on water can be added or can be subtracted. That can happen very readily. And so when that happens, we're left with a lot of OH ions. Whenever this is removed and it goes somewhere else, OH is left in place. So we have this thing called POH, which is also related to our pH. And it is very similar in calculation to our pH. It's negative log of your concentration of your OH minus ions. So moles per liter of OH. And what's interesting about this is it's the inverse of our pH. So we can draw this relationship that our POH plus our pH gives us the full scale on the pH scale. So if I have a pH here of 1, that means my POH will be what's left over. So -1, so 13 would be my POH. So if I wanted to know how many OH ions were in this solution as well, my POH is 13, I could solve for this. Now I'm not going to ask you all to do this in class because we aren't going to be using inverse logs. I'm not going to ask you to do that. But I did want to show you the relationship here that you can go from pH to POH, and you can convert these to H plus concentration and OH concentration and back and forth using all three of these equations. So you'll want to know these so that you can get back and forth between these values. Now the reason that our acid-base reactions are often called neutralization reactions is because when an acid and a base are at pH 7, they're neutral. So if you mix an acid of equal strength with a base of equal strength, they will effectively neutralize each other and arrive at a neutral pH of 7. So that is where that term neutralization reaction comes from, which just means an acid reacts with a base. That's all that term means. So let's give this a shot. See if you can write out the balanced equation for a neutralization reaction between this acid and base here. And then we'll go to the second part of it. So go ahead and write out the equation here, do the double displacement where you swap things, and balance out your equation to get your products so that you can see what's going on here. And then we'll go to number 2 afterwards. Okay, so let's look at the answer to this problem. So these are our reactants here, HNO3 and CaOH2. According to our double displacement reaction, which is how neutralization reactions work, we're going to swap our cations or our anions. Either one of those is appropriate. I'm going to do it this way. And we see that our products are CaNO3 plus HOH. Now you might be wondering why this 2 didn't follow over into our products, why that's not there. Because these subscripts stay with the compound that they are derived in. So we carry over the OH, but not necessarily the 2 of them. Now we determine our new subscripts on our products by looking at the charges. Remember our drop and swap from last time? So calcium's a 2+, nitrate is a -1, hydrogen is a +1, OH is a -1. This OH is a polyatomic ion. This is a polyatomic ion here as well. So we can determine what subscripts go here based on that. So this would be CaNO3 2 because of this charge here, our drop and swap. This one's fine because these charges balance out each other. So that's good. This is water. Okay. And this is our new product. Now it's time to balance out the equation now that we have our products and our reactants. So we can make sure that everything on the reactant side is on the product side by seeing how many atoms of each thing we have. So I'm going to go ahead and start with the nitrates here. So we have 1 nitrate on this side. We have 2 nitrates on this side, which means we need to double our amount to here. Our calciums are good. We've got 1 calcium on each side. We don't need to change that number. Let's check our OH groups now. So we have 2 OHs here. We only have 1 OH here. So I'm going to put a 2 here to help balance that out. And now I'm going to look at the hydrogens last. Again, you can do this in any order. This is just the order I've chosen to do it. So we've got 2 hydrogens here. These hydrogens don't count because they were included in the polyatomic ion OH. And we have 2 hydrogens here. So this is good. This is our balanced chemical equation. Okay, so now that we've done that, which of these compounds is the acid in this reaction? Which is the base? In order to do that, you need to see which of these compounds is giving an H+ ion away and which compound is receiving the H+ ion that was given in order to determine which one of these guys here in the beginning is an acid or a base. Let's take a look at the answer to this problem. So if we look here, what's happening is this is going away. So over here, we're swapping these, right? So we're giving the hydrogen to the OH. So this one donates, which makes it an acid. This one is accepting the H+. So it must be the base. Another good way to tell is that this has an OH in it. So it's probably a base. Again, that's not always true, but it happens to be for this one. And for a lot of examples, if there's an OH in it, it's usually a base. And this one has a hydrogen in the front. So it is also probably an acid. So those are 2 different clues that we can use. But this definitively determines whether or not it's an acid or base, is if it's donating the H+ or if it's accepting it. Now let's do some practice using our pH equation. I'm going to go ahead and write this up here so you don't forget it. H+ concentration, remember this is in moles per liter. Okay, so I'm going to ask you to solve this one. So whenever you maintain your pools, a lot of times you have to actually maintain the pH of the swimming water in it. So one of the chemicals that we can use to do this, to lower our pH in a swimming pool, is sodium bisulfate. This is what's often sold on the shelf in stores. So if you add 10 grams of the sodium bisulfate to swimming pool water in order to decrease the pH of the water, if there's 20,000 liters of water in the pool and no other chemicals, we're assuming that this is the only one affecting the pH and nothing else is affecting the pH. What will be the pH of the water after you add this NaHSO4? So we're going to go step by step through this one to solve it. So first things first, what would be the balanced chemical equation when you add this NaHSO4 to the water? What's going to happen to this ionic compound? How will it break apart in order to decrease our pH? So the thing that we learned about acids is that acids decrease pH by liberating H+ ions. So that's what's going to happen here. We're going to see that this NaSO4 loses its little hydrogen right here, plus H+. Now this step is important. There's still water left over. Because sometimes you can liberate more than one hydrogen. So think about this case if you had H2SO4 in water, you might release SO4 2- plus 2 hydrogens. So that's the reason this balanced chemical equation is important, is because we need to know how many moles of this stuff are liberated whenever the chemical is dissolved. Okay, so now I'm going to ask you, what is the molarity of the H+ ion? How many moles per liter of this do we have given the information in the problem here? So you can use unit conversion to solve for this. In order to figure out the molarity of the H+, what we want to do is we're going to take our given value here, 10 grams of our sodium bisulfates, NaH, SO4. We want to get to moles per liter, so we need to convert this value to moles. We do that using the periodic table. So you'll need to go to the periodic table and find the mass of your substance here in order to do this. So the mass is 120.06 grams per mole. It gives us 0.083 moles. Now remember, we want moles per liter, so we need it over our total amount of liters, which is 20,000. That's a lot of liters. Pools are quite big. So you take that value divided by the 20,000, you end up with 4.16 times 10 to the minus 6 molar of our H+. Okay, so now your next job is to find out what's the pH of the water. In order to do this, we use our equation, minus log of our H+ concentration in moles per liter. That's this guy here. So we plug it right in there. And you end up with 5.38. That's our pH. So that's how you solve for this problem. Let's take a look at our precipitation reactions. This is the other type of double replacement reaction that we had discussed. Or double displacement, it's the same thing. Sorry, I'm going to use those terms interchangeably. So this is our second type we're going to discuss. And what's unique about precipitation reactions, if you remember in lab this week, you mix two chemicals and a solid product formed. So we have two clear things. This is clear, this is clear, and when you mix them together, we see this entirely new chemical form, which is a solid, and oftentimes that is like cloudy kind of looking to us. So that raises the definition of if things that don't dissolve in water are called solids, the things that dissolve in water are called aqueous. So these are not liquids, they're aqueous. So things like table salt, NaCl, dissolves in water, so it is aqueous. We abbreviate that as AQ. Whenever you see a solid that's not soluble, like Ba2S, it's written as this for solids. So let's take a look at this precipitation reaction here. So we're going to predict the products here using our double displacement and figure out which of our chemicals in our product section are forming the white solid that you see here. So this is a white solid. So if you notice here, our BaCl2 is clear and it's being mixed with our lithium sulfate, and it is also clear. And it's not until they mix that this white solid is formed. So in order to do double displacement, we swap our cations right here. Okay, so we end up with BaSO4 plus lithium chloride. Now we need to balance this. Actually, let's determine our subscripts first. Sorry. So Ba is 2 plus, sulfate is a 2 minus, lithium is a plus, chloride is a minus. Okay, so we're actually good here. We don't need to add any subscripts. They all balance each other out. We do need to balance the chemical equation though, because if you notice there's a 2 here. So that means, oh, there should also be a 2 here. Sorry, that's a typo. That means we should have a 2 here in order to balance out this equation. Okay, so this is the balanced double replacement reaction here. Now the question is, which of these ones is the solid? Is it the barium sulfate or is it the lithium chloride? Which one is turning this white stuff? So in order to figure this out, we can go to our solubility chart. This solubility chart is going to tell us which things are solid and which ones are not. So if you look here, this stuff in yellow is our soluble compounds. So things that tend to have that have these ions inside of them. So anything with Na plus in it is always going to be soluble. Anything in that group 1 on the periodic table is soluble. NH4 plus is soluble. Nitrates are, Acetates are HCO3 minus. Here we go. This is what we used in the example problem, Cl minus and SO4 2. So Cl minus is always soluble unless it occurs, one of these exceptions occurs. So these exceptions are a couple of specific metals: silver, lead, copper, and mercury. Hg2 is mercury. So let's go back here and see if any of our chlorides are mixed with these substances. So we've got a chlorine here. It doesn't have silver, copper, lead, or mercury in it. Same here. No silver, copper, lead, or mercury. Also, lithium is always soluble, and there are no exceptions to that. So it's definitely not this one, which probably means it's our barium sulfate. So let's go back. So see how lithium here is always soluble, no exceptions. No exceptions listed here. So if we go down to our sulfates here at the very bottom, we see that sulfates are soluble unless combined with silver, calcium, strontium, barium, or lead. And our example here has barium in it, so it qualifies. So this is our white solid. So if I were to write out this equation with all of the states of each of these chemicals, this one here would be a solid, and all of these other ones would be aqueous because they dissolved in the water that's present. So our white solid here is barium sulfate. Now I'm going to task you with doing the same thing. So write a balanced chemical equation for the precipitation reaction of lead nitrate and iron chloride. Then I'm going to ask you to identify the solid, but that will be step 2. So go ahead and just do your double displacement reaction on this here and balance it. Let's take a look at how to balance this chemical equation. So we're going to swap our cations here, and we end up with PbCl plus FeNO3. Now we need to figure out our subscripts here, if we have any, if anything goes there. So we need to figure out the charges on our cations and anions. So lead and iron are transition metals. They're in that center category of periodic table. So we don't know what charge they have just by looking at them. So we have to figure it out based on their anions. So nitrate is a -1 here. Because there's 2 of these -1s, it must mean that our lead is a 2+. Because of the drop and swap. You drop that charge and swap it over to the other side. Our iron here could be iron 2+, iron 3+, iron 1+, we don't know. What we do know is we know that chloride always has a -1 charge on it. So in order for there to be 3 chlorides, there must be 3+ on the iron. So those are the charges that we can carry over to the other side. So we've got lead 2+ and a chloride minus, which means that we have a 2 here in order to balance those charges. Iron 3+, NO3 minus. So this must be NO3, 3. Now we can balance our equation. So I'm going to look at the chlorides first because that's just what I choose. We've got a 3 here and a 2 here. Those are unbalanced, so I'm going to put a 3 here and a 2 here. It gives me 6 chlorides on each side. So 2 times 3 and 3 times 2 are the same thing. So I now have the same amount of chlorides on each side. 6Cl, 6Cl. Okay. Now let's take a look at our irons. That gives us 2 irons here. We have 1 here, so we're going to need to double that number. You might also draw that conclusion by saying that we have 2 and 3. So if we've got a 3 and a 2, it gives us 6 nitrates, 2 irons. So 2 irons. We have 6 nitrates now, 6 nitrates. We have 6 nitrates over here. 2 nitrates. I apologize. I was about to stick a 3 right here because we have 3 leads. So now we have 6 nitrates. Now we have 6 nitrates. We have 3 leads. Okay. So this equation is balanced. Now I'm going to ask you to look at your products here. this 3PbCl2 and 2FeNO3, 3, and figure out which one is this yellow stuff, which one is our solid. So I'm going to flip back to the solubility chart so that you can work on this question yourself. So your equation was PbCl2 plus iron nitrate, iron 3 nitrate. So which one of these two is your solid? In order to figure this out, we need to look at our anions. So our first anion here is chloride. So we're going to check out chloride over here. It's soluble unless it's combined with one of these exceptions. And for us, fortunately, it is. It's combined with lead. So that's definitely our solid. If we want to check out iron, we need to look at our nitrate. Since there's no cations really on this chart except for ammonia and these here, it's mostly anions. So you're usually going to be looking at anions in order to figure out what's on this chart. So nitrates are over here, and these are always soluble, no exceptions. So that means that that one's definitely soluble. So this one is aqueous, AQ, and this one is our solid. That's how you answer this question. Something else that I did want to mention before we head out is that sometimes these reactions won't have solid products. So the one that I showed you at the beginning, we need to take a look at. I'd like to revisit. So we had NaCl plus KBr. We swapped our cations to give us KCl plus NaBr. If we go back to our solubility table, what you're going to find is all of these products, or all of these reactants, and all of these products are aqueous. So essentially what that means is that there's no reaction here. Because there's no solid being formed, and we're going to see in the next part of this topic that if we write out our net ionic equation for this reaction, there's actually not anything going on. So we're going to explore that in the next video. But just know that if everything is aqueous in your equation, that means there's no reaction happening. There must be a solid in order for us to consider that a reaction has happened.